Welcome back to the Deep Dive. Today we are moving past the glossy screens and the smooth animations and plunging straight into the engineering challenge at the very core of every modern application.
Yeah, we're talking about how you manage to do, 1,000 things at once without the whole house of cards collapsing.
Exactly. We are talking about concurrency.
That's right. We're dissecting the tools Apple gives us, to build applications that are fast, responsive, and stable.
And this is going to be a technical deep dive. We've got a comprehensive stack of sources covering everything from the low-level system hooks of Grand Central Dispatch, GCD, all the way up to Swift's modern async await.
The whole evolution. And our mission today, it's pretty straightforward, but, ambitious, I guess. We are synthesizing these core concurrency models for you, the learner.
So by the end of this conversation, you should understand the why behind these tools, how they fit together, and crucially, which one you should be reaching for.
Yeah, depending on the problem you're trying to solve, right? For performance, responsiveness, safety.
Got it. And to really appreciate where we are now, we kind of have to start at the beginning. The before picture.
Oh, absolutely. Before Apple introduced robust system-level tools like GCD, handling concurrency was, it was a developer's nightmare, honestly.
How so? What were people doing?
You had to manually create and manage threads, directly, using things like NSThread or even older PuseSX thread, super low-level stuff.
Wow. Okay, so that sounds complicated. It's not just starting a job in the background, is it?
Not at all. You were responsible for literally everything. You had to handle synchronization yourself. Think manual locks, semaphores, mutexes, trying to prevent data corruption. Yeah. And you were constantly dealing with the massive CPU cost of context switching. You had to worry about scheduling the threads, and you were constantly trying to anticipate and fix those really nasty bugs.
Like deadlocks and race conditions.
Exactly, those deadlocks where everything just grinds to a halt, and race conditions where the results are just unpredictable because threads are trampling over each other's data. It was manual, high-stakes complexity baked into everything.
The mental overhead must have been huge.
Enormous. And the apps, often unstable, unpredictable, because the system just didn't have enough control over how resources were being used. A thread, it's an expensive resource.
Threads POW. Like memory?
Both memory and CPU. Each thread needs its own stack space, which adds up. And then there's the constant scheduling overhead for the CPU. It was just inefficient at scale.
Okay, so that mess leads us directly to the first major revolution in Apple's approach. Grand Central Dispatch. GCD, you said it changed the game.
Fundamentally, yeah.
So what is GCD exactly, and why a low-level C API? That seems kind of hardcore.
It is pretty low level, and that's intentional for performance. GCD is Apple's high-performance C API for managing concurrent operations. The key thing is it talks directly to the OS kernel, bypassing layers of abstraction. And it completely abstracts away the concept of threads for the developer. You stop thinking about threads. Instead, you submit tasks, basically just blocks of code, to dispatch queues.
And the system figures out the rest, the when and where.
Exactly. The system, GCD, decides when and on which underlying thread your code actually runs. It takes that burden off your shoulders.
Right, shifting responsibility to the OS, which is obviously much better positioned to manage resources globally.
Precisely.
Our sources point to 4 big benefits. The first you mentioned is just simplification. No more manual thread juggling.
Absolutely. That's huge for developer productivity. But the really big architectural wins are in performance and resource management.
How so?
Well, GCD manages this efficient, centralized pool of worker threads for the entire system. That means overall performance is way better than if every single app tried to manage its own threads separately. You avoid contention.
And the system is smarter about the device's overall health too, right? Like battery life.
Exactly. That's the third benefit. Much better resource utilization. GCD is dynamic. It constantly adjusts the number of active threads based on current system load, the CPU architecture, even how hot the device is getting.
So if the phone's overheating, GCD can throttle things back.
Across all apps, yeah. Something a single developer managing their own threads could never coordinate. And the fourth benefit is prioritization. Crucial for UX.
Make sure the important stuff happens first.
Right. It ensures critical tasks like UI updates run immediately and sequentially on the main queue, while heavy background stuff like networking or processing data gets pushed to background queues.
That dynamic management you mentioned, that's key to solving one of the biggest problems of the old way, the thread explosion problem. Can you unpack that a bit?
Sure. Think back to manual threads. If you needed to handle, say, 10 network requests concurrently, a common pattern was just create 10 threads.
Okay, seems simple enough.
Maybe for one user, but scale that up. Imagine a popular app with millions of users. If each one spins up even 5 or 10 temporary threads every time they do something, you suddenly have potentially millions or tens of millions of threads across the entire OS.
Whoa. Okay, I see the explosion.
Yeah.
What does that actually do to the system?
It grinds it down. First, massive memory usage because every thread needs that stack memory we talked about. But worse is the CPU overhead.
From context switching.
Exactly. The CPU starts spending almost all its time just saving the state of one thread and loading the state of the next thread over and over again. It's not actually doing the work your app needs. Performance just tanks.
So how did GCD prevent this explosion?
It uses a thread pool. The system maintains a limited, carefully managed pool of worker threads. The size of this pool is optimized based on the hardware, number of cores, etc.
So it doesn't just create a new thread for every task you submit.
Nope. It acts like a funnel. You submit your tasks to queues. GCD then takes tasks from those queues and maps them onto its available pool of worker threads.
Reusing threads.
Constant reuse. When a thread finishes a task, it doesn't die. It immediately goes back to the queue and asks, what's next? This dynamic reuse of a limited pool prevents the system from being overwhelmed. It's all about efficient resource management baked into the OS.
Okay, so we interact with this GCD system primarily through dispatch queues. And the basic idea is simple. A queue manages tasks, these blocks of code, in a FIFO order, right? First in, first out.
That's the fundamental principle, yeah. But how those tasks execute depends on the type of queue. We usually break them into 3 categories.
Let's start with the first type, serial queues.
Serial queues are all about control and predictability. They execute only one task at a time and strictly in the order they were submitted. Task A finishes completely before task B even starts.
And the main reason you'd use one, the superpower really, is thread safety.
Absolutely. That's the killer feature. Because only one task from that specific serial queue can run at any given moment, you get built-in thread safety for shared resources.
Like what kind of resources?
Anything mutable that multiple parts of your code might try to change at once. Think updating a shared variable, writing to a configuration file, modifying some shared data structure like a dictionary. With a serial queue, you don't need manual locks. The queue enforces serialized access.
Okay, makes sense. So that's control. What about speed? That brings us to concurrent queues.
Right. Concurrent queues are built for parallelism and throughput. They can execute multiple tasks at the same time, potentially using multiple CPU cores if available.
So tasks still start in FIFO order.
They are dequeued in FIFO order, yes, but they can run concurrently. The critical difference is the order of completion isn't guaranteed. Task B might actually finish before Task A, even if A was submitted first just because B was shorter or got scheduled differently.
And these are good for
tasks that are independent of each other, things you can break down and run in parallel, processing multiple images, hitting several network endpoints at once, performing calculations on different data sets, anything where the order of finishing doesn't mess things up.
Got it. And the third category covers the special queues the system provides.
Yeah, these are the ones you'll use most often. First, the super important main queue. It's special because it's always serial, and it's tied directly to the application's main thread.
The UI thread.
The UI thread, exactly. Then you have the global queues. These are shared concurrent queues provided by the system itself. They come pre-configured with different priority levels, which we'll get to.
Called quality of service, right?
Right, QoS. And finally, you can also create your own custom queues. You can define these yourself as either serial or concurrent, depending on whether you need synchronization or parallelism for your specific logic.
Let's dig into that main queue for a second. Every iOS developer learns this rule early. UI updates must happen on the main queue. Why is that rule so absolute?
It's fundamental because the UI frameworks, UIKit on iOS, AppKit on macOS, even SwiftUI's rendering, they are simply not thread safe. Meaning, if you try to change UI elements from multiple threads simultaneously, things will break. Badly. Imagine 2 background threads trying to update the text in the same label, or change the position of a button at the exact same time.
Chaos.
Total chaos. The underlying drawing system gets corrupted. You'll see visual glitches, weird animations, corrupted state, or more often than not, your app will just crash. The main thread is specifically designated to handle all user interactions, touches, gestures, scrolling, plus all the drawing and animation updates. These things need guaranteed sequential access to maintain consistency.
So if I'm doing some heavy lifting in the background, say downloading and parsing a big chunk of JSON,
Yep.
When that finishes, I have the data, but I can't just update my table view directly from that background thread.
Correct. You absolutely must dispatch back to the main queue. The standard pattern is dispatch_queue.main.async. Inside that block, you can safely update your labels, reload your table view, whatever UI changes you need.
And using async there is important too, right?
Yes. Async ensures your UI update task is added to the end of the main queue's current work. It doesn't block the background thread, and it waits its turn on the main thread, ensuring it runs smoothly after any ongoing drawing or event handling. It's the essential bridge.
Okay, perfect. Now, you mentioned the global queues have different priority levels. That brings us to quality of service, or QoS. This is how we tell GCD what's important.
Exactly. QoS is the hint you give the system about the nature and importance of the work you're submitting. The system uses this hint to prioritize tasks, allocate CPU time, manage I/O bandwidth, and even make decisions about power consumption.
So picking the right QoS is pretty important for both performance and battery life.
Crucial. Using the wrong QoS can lead to sluggish UI if background work is prioritized too high, or slow background tasks if they're too low. Let's run through the levels, top down. Highest priority is user interactive.
Okay, what goes here?
This is strictly for tasks that are directly involved in manipulating the UI right now and need instantaneous results. Think handling a continuous touch gesture like scrolling, driving an animation update, reacting immediately to a button tap that needs to feel instant.
So very short, very critical tasks.
Extremely short and lightweight. If you put a heavy calculation here, you'll freeze the UI because the system gives it maximum resources, assuming it will finish in milliseconds. Don't do that.
Got it. Next down the ladder is user-initiated.
This is for tasks the user explicitly started and is actively waiting for, but maybe not within a single animation frame. Loading data needed to populate the screen after a tap, opening a document, performing a quick filter or search the user triggered. They expect results fairly quickly, maybe within a few seconds.
Okay. Then we have utility. Sounds like longer background stuff.
Exactly. Utility is for long-running tasks where the user has initiated it, but they aren't necessarily staring at a spinner waiting for it right now. Think downloading a large file, importing a big data set, doing complex processing that might take seconds or even minutes. Progress might be shown, but immediate completion isn't critical.
The system gives these less priority than user-initiated work.
Yes, lower priority and often a more constrained energy budget to save battery. And finally, at the bottom, we have background.
What lives here?
Tasks the user is completely unaware of. Things the app does proactively or for maintenance, maybe prefetching data for later, syncing local data with a server in the background, cleaning up temporary files, indexing content. These run with the lowest priority, often when the device is idle or plugged in.
And what if you don't specify any QoS?
It falls back to default. The system tries to infer the QoS, and it often lands somewhere between user-initiated and utility. But honestly, it's always best practice to be explicit. Think about how the task impacts the user and choose the appropriate QoS.
Okay, so we have queues and priorities. Now let's talk about how we submit work. Synchronous, sync, versus asynchronous, async. This is fundamental to controlling the flow.
Absolutely. Core concept. Let's start with sync. When you dispatch a task using sync, two things happen. One, the task runs immediately if the queue's thread is available. Two, and this is the critical part, your current thread blocks.
Blocks, meaning it just stops right there.
Stops dead in its tracks. It waits until the task you submitted to the queue finishes executing and returns. Only then does your original code continue to the next line.
When would you actually want to block a thread like that? Seems dangerous.
It is dangerous if misused, but it's occasionally useful for very quick tasks where you absolutely need the result before proceeding, or for specific synchronization patterns, maybe ensuring some setup code on a serial queue finishes before anything else touches it. But generally, you avoid sync for anything long.
Because async is the go-to for responsiveness.
Exactly. Async is your workhorse for anything that might take time networking, file I/O, heavy computation. When you dispatch async, the task is submitted to the queue, but your current thread does not block.
It just keeps going.
Instantly returns and continues executing the next line of code. The task you submitted runs later, in the background, on one of the queue's threads, completely independently. This keeps your calling thread, especially the main thread, free and responsive.
Okay, now you mentioned sync is dangerous. Let's talk about the big trap, deadlock. Specifically, calling sync onto the same serial queue you're already running on.
The classic GCD deadlock. Yes, this is a mistake everyone makes at least once. Imagine you're currently running code inside a block that was dispatched to a specific serial queue. Let's call it my serial queue.
Okay, I'm executing on my serial queue.
Right. Now, inside that code block, you make another call, myserialqueue.sync, some other work. You're trying to synchronously dispatch more work onto the same serial queue. Deadlock. Instantly. Because my serial queue is serial, it can only run one task at a time. Your current task is running, occupying its single thread. The sync call tries to schedule the new task onto my serial queue, but it can't start because the queue is busy with your current task.
And the sync call blocks the current task.
Waiting for the new task to finish. But the new task can never start because the current task, which is waiting, is holding the queue's thread hostage. It's a circular wait. The queue waits for the task waits for the queue, everything freezes.
Ouch. Okay. So rule number 1, never call sync targeting the serial queue you are currently executing on.
Pretty much sums it up. Use async instead or dispatch sync to a different queue and absolutely necessary.
Right. Okay, moving on from dispatching individual tasks to coordinating multiple tasks. Sometimes you need to run several things concurrently and then do something only when they're all done. That's where dispatch groups come in, right?
Exactly. Dispatch groups are perfect for that fan-out, fan-in pattern. You kick off multiple asynchronous tasks, maybe fetching different pieces of data from various network endpoints or processing chunks of a file in parallel. The group lets you track all these independent operations as a single unit.
How does it track them? Is it automatic?
Not quite automatic. You have to manually signal the group. Before you start an async task that belongs to the group, you call group.enter. This basically tells the group, hey, one more task is started.
Like incrementing a counter.
Precisely. And then, crucially, inside the completion handler of that async task, when it's totally finished, you must call group.leave. This decrements the counter.
So you had to balance the enters and leaves perfectly.
Absolutely perfectly. Forget a leave, and your group will wait forever because the counter never reaches 0. Call leave too many times, and you'll likely crash.
Okay, assuming I get the balance right, how do I know when everything's done?
That's the group.notify function. You provide it with a queue, usually dispatch queue.main, and a block of code. That notification block will only execute after the group's internal counter hits 0, meaning every single task that entered the group has also left it.
So notify is where you aggregate results or update the UI.
Exactly. It's way cleaner than complex nested callbacks or trying to manage completion flags manually. It's great for parallel network calls.
Okay, another coordination tool. Dispatch barriers. These sound a bit more specialized. You mentioned them for thread-safe data structures on concurrent queues, solving the reader-writer problem.
Yes, barriers are specifically designed to solve the classic reader-writer scenario, and they only work correctly on concurrent queues that you manage yourself, not the global concurrent queues usually.
Remind us of the reader-writer problem again.
Sure. You often have shared data, maybe a cache or some configuration settings. You want lots of parts of your app readers to be able to read this data concurrently for performance. But when you need to change the data a writer, that write operation must happen exclusively. No readers or other writers should be active during the write. Otherwise, you risk data corruption or crashes.
Right. Reading while someone else is writing is bad.
Very bad. So how do you allow fast concurrent reads but enforce safe exclusive writes? That's the barrier's job.
How does it work, technically?
You create your own custom concurrent queue. For read operations, you dispatch tasks to this queue using the standard async method. Multiple reads can happen in parallel, fantastic. But for write operations, you dispatch the task to that same concurrent queue, but this time you add the barrier flag to the async call, queue.async flag.
And what does that barrier flag do?
It tells GCD to do something special. First, GCD waits for all the tasks that were submitted to the queue before the barrier task, all the concurrent reads currently in flight, to finish completely.
So the queue drains of existing readers.
Exactly. Once the queue is empty of prior tasks, the barrier task, your write operation, executes exclusively. It runs all by itself. While the barrier task is running, any new tasks submitted to the queue, whether reads or other potential writes, are held off. They don't start.
Like putting up a temporary wall.
Perfect analogy. The barrier puts up a wall, does the write safely, and then when the barrier task finishes, the wall comes down and the queue goes back to processing subsequently submitted tasks concurrently.
That's clever. So reads happen concurrently, writes happen exclusively, all managed by the queue in the barrier flag.
Precisely. It gives you that thread-safe, mutable state on a concurrent queue without needing manual locks. But remember the big caveat. Barriers only provide this exclusive behavior on concurrent queues you create. They don't have the same effect on serial queues, where everything is already exclusive, or the global concurrent queues, where you don't have exclusive control.
Got it. Custom concurrent queue plus barrier flag for safe writing. Okay, one last GCD tool. Dispatchably. Sounds like apply. Like applying something multiple times.
Yeah, think of it as GCD's high-performance for loop. Dispatchably executes a given block of code a specific number of times, just like a loop.
Okay, so what's the big deal? Why not just use a for loop?
The key difference is how it executes those iterations. A standard for loop runs sequentially, one iteration after the other. Dispatchably, however, executes the iterations concurrently on a dispatch queue. You typically provide a concurrent global queue.
So it parallelizes the loop body.
Exactly. If you have, say, 1,000 items in an array and you need to perform some heavy independent calculation on each one, dispatchably can potentially run many of those calculations simultaneously across all available CPU cores. It can be dramatically faster than a simple serial loop for computationally intensive tasks.
Like image processing on a batch of thumbnails or complex data transformations.
Perfect examples. Anything that's embarrassingly parallel where each iteration is independent.
Is it async or sync in terms of when it returns?
Good question. Unlike dispatch-async, dispatchably behaves synchronously. The call to dispatchably itself will block the thread it was called on until all of the iterations have completed.
Okay, so it parallelizes the work, but waits for it all to finish before continuing.
Right, which is often what you want. You need all the processing done before you move to the next step that depends on those results. Okay, we spent a lot of time deep in the C-based world of GCD dealing with blocks and queues. Now, let's shift gears significantly and talk about ends operation and ends operation queue.
Right. This isn't replacing GCD as it is built on top.
Exactly. Think of ends operation queue as a higher-level, object-oriented abstraction layer built directly on top of GCD. GCD is the engine. Ends operation queue is more like the sophisticated control system you can put around it.
So why introduce this extra layer? If GCD is so powerful and efficient, why bother with ends operation? What does the object-oriented approach give us?
It gives us features that are difficult or cumbersome to implement with raw GCD blocks. Because an ends operation is a proper object, it can have state, it can be subclassed, and it supports more complex workflow management capabilities.
Okay, like what? What are the key advantages?
The big one, arguably the most powerful feature, is operation dependencies.
Dependencies, meaning you can make one operation wait for another.
Precisely. You can establish explicit relationships. You can say, Operation B cannot start until Operation A has finished. Or even, Operation C needs both A and B to complete first.
How do you set that up?
It's simple. You just call Operation B add dependency, Operation A. The ends operation queue automatically respects these dependencies when scheduling tasks. It guarantees the execution order you define, regardless of queue priorities or when the operations were added.
Wow, okay. Trying to orchestrate that with just GCD groups and notifies would be messy.
Way messier and much more error-prone, especially for complex multi-stage pipelines. Think of a video processing workflow. Download, decode, apply filter, encode, upload. Dependencies make that chain explicit and robust.
What else does the object model give us? Cancellation?
Yes, built-in cooperative cancellation support. Since end operation is an object, it has a standard cancel method. You can call this from anywhere.
And the operation just stops.
Well, it's cooperative. Calling cancel sets an isCanceled flag on the operation. Inside your operations code, especially in custom subclasses, you need to periodically check this flag. If isCanceled is true, your code should clean up gracefully and stop executing.
So it doesn't just magically halt at mid-execution.
No, but it provides the standard mechanism and flag. This is still miles better than GCD, where canceling a dispatch block is extremely difficult, often impossible once it started running.
Okay. Dependencies, cancellation. What else? You mentioned state?
Right. Operations have observable state. They are KVO compliant.
KVO. Key value observing.
It's an old-school COCO pattern, but powerful here. It means you can observe properties on the ends operation object like is executing, is finished, is canceled. Your code can get notified automatically whenever the operation's state changes.
So you don't have to keep asking the operation, are you done yet? Are you done yet?
Exactly. No polling needed. This is great for updating progress bars, logging lifecycle events, or triggering other logic based on an operation's progress. GCD blocks don't really have this kind of observable lifecycle state.
Makes sense. And ends operation has its own priority system too, distinct from QoS.
It does. You can set a queue priority on each ends operation, ranging from very low to very high. This helps the ends operation queue decide which ready operation, meaning its dependencies are met, to start next. It's a different layer of prioritization operating within that specific queue, separate from the system-wide GCD QoS, which influences which queue gets CPU time from the OS.
So you could have high QoS background work containing operations with varying internal priorities.
You could, yeah. It gives you finer-grained control within a specific set of related tasks.
And finally, queue-level control, like pausing.
Yes. An entire ends operation queue can be suspended. You just set queue.isSuspended equals true. When suspended, the queue stops starting new operations. Operations already running will continue to completion, but no new ones will begin until you set isSuspended back to false.
That sounds useful. Like if the app goes in the background, maybe pause all network operations.
Perfect use case. Pause downloads when backgrounded, resume them cleanly when the app comes back to the foreground. You can't really suspend a GCD queue in the same way, at least not the global ones. This gives ends operation queue much better high-level workflow management.
Okay. When we actually use this, what kinds of ends operation objects do we work with?
Mostly two types. The simplest is block operation. As the name suggests, it just wraps one or more code blocks, closures. It's easy to use for straightforward tasks when you want to leverage the ends operation features like dependencies or cancellation without creating a full subclass.
And for more complex stuff?
For anything non-trivial, especially operations that involve asynchronous work within the operation itself, like waiting for a network callback, or need fine-grained control over state transitions and cancellation checks, you'll create a custom ends operations subclass.
That sounds more involved.
It is. You typically override the main method for synchronous operations or manage the isExecuting and isFinished properties manually for asynchronous operations. It gives you maximum power and flexibility, but requires careful implementation to get the state management right.
Okay, so we've seen the C-level power of GCD and the object-oriented control of ends operation. But both ultimately rely heavily on completion handlers, delegates, callbacks.
The callback pattern.
And as apps got more complex, this led to what developers lovingly call callback hell, or the pyramid of doom.
Oh, yeah. Deeply nested closures where error handling becomes a nightmare, readability goes out the window, and just reasoning about the control flow is incredibly difficult. You pass a closure to a function, which calls another async function and passes another closure, and so on.
It gets indented further and further across the screen.
Exactly. It's brittle and hard to maintain. This complexity was a major driving force behind Apple introducing the biggest shift in concurrency in years, the Swift concurrency model.
Built around async and await.
Those two keywords change everything. An async function is simply a function marked as potentially performing asynchronous work. The key thing it allows is suspension.
Suspension. Meaning it can pause without blocking.
Precisely. An async function can pause its execution at an await point, allowing the thread it was running on to go off and do other work. It doesn't block the thread like sync does.
And await is the keyword that marks those pause points.
Correct. When your code reaches an await call to another async function, you're explicitly telling the Swift runtime, okay, pause execution of this function right here. Go run that other async function. When it eventually finishes and gives me a result or throws an error, then come back and resume execution from this point.
The magic is that the code still looks linear, right? Like synchronous code.
That's the genius of it. Your asynchronous code reads top to bottom, no nested closures. You call an async function, await its result, use the result on the next line. It looks synchronous, but it behaves asynchronously under the hood, freeing up threads during the waits.
And error handling.
So much cleaner. Async functions can be marked with throws. You use a standard do, try, catch block around your wait calls, just like synchronous error handling. No more complex result types passed into completion handlers or optional error parameters to check. It's unified and much easier to reason about.
This readability and structure is tied to a concept called structured concurrency. What does that mean?
Structured concurrency is about bringing order and predictability to asynchronous tasks. It imposes a hierarchy, a clear structure.
Oh.
The core idea is that every asynchronous task created within a certain scope has a parent task, and the lifetime of the child task is strictly bound to the lifetime of its parent. A parent task cannot complete until all of its child tasks have completed.
Okay, what are the practical benefits of that structure? Seems a bit abstract.
It has huge safety benefits. First, no more leaked tasks. With older fire-and-forget approaches like dispatchqueue.global.async, a background task could keep running long after the function that launched it had finished, potentially holding onto resources or causing weird side effects. Structured concurrency prevents this. Child tasks are automatically contained within their parent's scope.
Okay, so better resource management. What else?
Better error handling. If a child task throws an error, that error automatically propagates up to the parent task where it can be caught and handled. You don't lose errors in the void. And third, automatic cancellation. If a parent task is canceled, the cancellation signal automatically propagates down to all of his child tasks and their children.
Oh, wow. So canceling one thing reliably cancels the whole tree of work it started.
Exactly. It cleans itself up automatically, saving resources and preventing unwanted work. The entire execution graph becomes predictable and manageable.
How do we actually create and manage these structured tasks in Swift?
The basic unit is a task. You can create one explicitly, like task, await, do something. This starts a new top-level task, or a detached task if needed. But more often, you work within the structure provided by async functions. For running things concurrently within that structure, you mainly use two tools.
Which are?
Asynclet bindings and task group.
Okay. Asynclet, when do I use that?
Use asynclet when you know at compile time exactly which independent asynchronous operations you want to run in parallel. Say you need to fetch user details and their list of friends simultaneously. You'd write asynclet user, fetch user details. Asynclet friends, fetch friend list. Maybe do some other work here. Let profile await make user profile, user friends.
Ah, so they both start running immediately and in parallel when you declare them with asynclet.
Yep. And then later in the code, when you actually need the results, you await them. It's super clean for a fixed number of parallel tasks.
And task group is for when you don't know how many tasks ahead of time.
Correct. Task group is the tool for dynamic parallelism. Imagine you fetch a list of photo IDs, and now you need to download the data for each photo concurrently. You don't know how many IDs you'll get back.
Right.
You'd create a task group, loop through your IDs, and inside the loop, call group.addTask, await download photo for each one. The group manages all these dynamically created child tasks. You can then iterate over the group to collect the results as they complete, or wait for them all. It ensures all added tasks complete before the group scope exits.
Very cool. Okay, structured concurrency makes async code cleaner and safer. But what about the other big concurrency headache? Data races. Accessing shared mutable state.
Ah, yes, the bane of multi-threading. GCD and NS operation give us tools to manage this: serial queues, barriers, locks, but they required careful manual application. Swift concurrency introduces a language-level solution: actors.
Actors, what are they fundamentally?
An actor is a special kind of reference type, like a class, specifically designed to protect its internal mutable state from concurrent access, thereby preventing data races by construction.
Preventing them by construction. How?
An actor ensures that only one task can access its mutable state, its properties and methods that change things at any given time. It achieves this by serializing access to its internal state.
So it's like having an invisible serial queue protecting everything inside the actor.
That's a good analogy, but it's more deeply integrated. The key is compiler enforcement. If you try to access a mutable property or call a mutating method on an actor instance from outside the actor itself, the Swift compiler forces you to use await.
So await isn't just for pausing for async work. It's also required to cross the boundary into an actor.
Exactly. That await signals a potential suspension point because your code might have to wait its turn to get exclusive access to the actor's state. The Swift runtime manages a kind of mailbox for each actor, processing incoming calls one at a time, ensuring only one task is inside the actor modifying state at any moment.
So actors don't just give you a tool to prevent race conditions like a lock or a barrier. They make race conditions on their state structurally impossible at the language level.
Precisely. By isolating their state and forcing asynchronous, serialized access from the outside via await, actors provide thread safety by default for the data they encapsulate. It shifts the burden of ensuring data safety from the developer's discipline to the compiler and runtime. This is a massive leap forward for writing correct concurrent code.
Okay, before we wrap up and put all this together, let's clarify two terms that often get confused. Concurrency versus parallelism. They sound similar, but they're not the same thing.
Very important distinction. Yeah, they're often used interchangeably, but they mean different things. Concurrency is about dealing with or managing multiple tasks over a period of time. It's about structure. Tasks can start, run, and complete in overlapping time periods, but they don't necessarily have to be running at the exact same instant.
Like juggling. You're handling multiple balls, making progress on each one, but only touching one ball at any given microsecond.
Excellent analogy. On a single CPU core, concurrency is achieved by interleaving, rapidly switching between tasks. It gives the illusion of doing multiple things at once. The focus is on efficient task management and responsiveness.
Okay, so what's parallelism then?
Parallelism is about actually doing multiple things at the exact same instant in time. It requires hardware with multiple processing units, like a multi-core CPU. Parallelism means task A is running on core 1 at the same time that task B is running on core 2.
So multiple jugglers juggling their own balls simultaneously.
Perfect. The focus of parallelism is raw speed and throughput, getting more work done in the same amount of wall clock time by executing tasks simultaneously.
So tools like GCD and ENS operation queue help us manage concurrency. And if we run our tasks on concurrent queues on a multi-core device, they can leverage the hardware to achieve parallelism.
Exactly. You structure your work using concurrency primitives, and the system executes it with parallelism if the hardware allows. Swift's structured concurrency and actors also manage concurrency, and the underlying system will still try to execute independent tasks in parallel.
Got it. Now, one more slightly lower level GCD thing we should probably mention briefly is dispatch source. What's that used for?
Dispatch source is a more advanced GCD feature. It's a really efficient way to monitor various kinds of system events without needing to dedicate a thread to polling or blocking.
What kinds of events?
Things like timers, very precise ones, Unix signals like process termination signals, file descriptor events, is there data ready to read from a socket, can I write to a file system changes, did a file get deleted or renamed, process events, did a child process exit.
So it's like setting up listeners for low-level system happenings.
Exactly. You configure a dispatch source for the event you care about, give it a queue and an event handler block, and the system will automatically schedule your block on that queue whenever the event occurs. It's very efficient for building responsive, event-driven systems.
Okay, cool. Good to know it exists.
Yeah.
Now, let's zoom way out. We've talked about all these tools, GCD, ENS operation, tasks, actors. How does this fit into the bigger picture of application architecture, like the classic model view controller MVC pattern?
Right. MVC is all about separating concerns. You have the model, your data, your business logic, the core stuff of your app. Think user objects, data persistence, network fetching logic.
Then the view. The UI elements, what the user actually sees and interacts with. Buttons, labels, tables. Should be pretty dumb, mostly just displaying things.
Yep. And the controller, or often view model in MVVM or similar patterns, acts as the mediator. It takes user input from the view, translates it into actions on the model, gets data back from the model, and formats it for the view to display.
And the common trap, especially in UIKit, is the massive view controller problem.
The infamous MVC equals massive view controller. Yeah. This happens when the controller starts doing way too much. It's not just mediating, it's doing the network calls directly, parsing the JSON, managing complex state, handling all the concurrency itself. Often all tangled up with the UI code.
And probably blocking the main thread while doing it.
Often, yes, leading to an unresponsive, slow application. So the architectural guidance here is clear. Keep your heavy lifting out of the controller view model.
Where should it go?
That heavy work, fetching data, parsing, complex calculations, file I/O, belongs primarily in your model layer, or perhaps in dedicated service objects that the controller view model uses.
And that's where we should be using GCD, ENS operation, tasks, actors, inside the model or service layers.
Absolutely. You initiate the asynchronous work there. Fetch data using a task. Parse it using dispatchably, maybe. Protect shared model state with an actor. The model service layer does the work asynchronously, off the main thread.
And then how does the result get back to the UI?
The model service layer eventually provides the result back to the controller view model, often using completion handlers in the old world, or simply by returning from an async function in the Swift concurrency world. The controller view model then takes that final process data and, critically, jumps back onto the main thread, dispatch queue.main.async or at main actor, just for the brief moment needed to update the view.
So async work happens deep in the model service layers. UI updates happen briefly on the main thread via the controller view model. Keeps everything clean and responsive.
That's the goal. Clear separation of concerns and keeping that main thread free for UI interactions. Hashtags, hashtag outro.
Wow, okay. We really covered a huge amount of ground today. We traced the whole evolution of concurrency on Apple platforms, didn't we?
We definitely did. Started right down at the foundations with GCD, low-level C API using queues serial for safety, concurrent for speed, and that vital concept of the system managing a thread pool to prevent explosions. And we looked at its coordination tools, dispatch groups for knowing when multiple async tasks are all done, and dispatch barriers for that clever reader-writer lock pattern on concurrent queues.
Then we moved up a level to the object-oriented world of N's operation queue, recognizing how its features dependencies, cancellation, observable state via KVO, queue priorities, suspension make it better suited for managing complex multi-stage workflows.
A great abstraction on top of GCD for those structured pipeline scenarios.
And finally, we landed in the modern Swift era. Async and await completely transforming asynchronous code, making it look linear and manageable. Structured concurrency bringing safety and predictability with task hierarchies and automatic cancellation.
And actors providing that groundbreaking built-in protection against data races by isolating state and enforcing access through await, really solving one of the hardest problems in concurrency at the language level.
Understanding the strengths and weaknesses of each of these paradigms, GCD's raw power, N's operations workflow control, Swift concurrency's safety and readability is absolutely crucial for you, the listener, when you're building apps.
Yeah, because choosing the right tool directly impacts how responsive your app feels, keeping heavy work off that main thread, and how stable it is by preventing those nasty race conditions and deadlocks.
The journey itself tells a story, doesn't it? From GCD, which gives you immense power but demands immense discipline, towards actors, which offer perhaps less fine-grained control but provide powerful structural guarantees about correctness.
It's definitely a trend across the industry, prioritizing safety and reducing bugs through language and system design, sometimes even at the cost of some raw performance flexibility.
Which brings us to our final thought for you to chew on. When you're designing the core parts of your next complex application, the objects that hold the important mutable state, the services that manage critical data, where does your architectural focus land?
Do you reach for the maximum performance and low-level control offered by GCD, accepting the challenge and inherent risks of manually implementing thread safety with barriers, queues, or locks?
Or do you lean towards the built-in safety, the enforced correctness, and the improved readability you get from Swift's actors, accepting that accessing that protected state will always require an await? That trade-off between explicit control and enforced safety is a defining choice in modern app architecture.